Okay, so good evening, guys. I hope I'm audible. So let's start the class then. I'm recording. I've started the recording. Okay. So let's go back and see what we did last class. So we covered Fermat's theorem and Euler's theorem and did a few bunch of exercises. Quadratic residues also. And there were three problems given as homework, right? So did any one of you try out these three problems? Uh, like the first one seems easy, so it's of course doable. Second one is a bit tricky, but still pretty easy. Third one is a bit difficult since you need another result Wilson's theorem to show it more easily. I'm sure there are other ways to show it too. So let's try with the homework problems. So solution. First one is easy, so one of you must tell me what to do or how to proceed. So let me ask Aman Kumar. Yeah. Aman Kumar, can you unmute, please? Hello, Aman.
Yeah,
Yeah, so how should we proceed to find the last two digits of 7 per 100 minus 3 per 100?
we can consider modular 100 here.
Yeah, so we need to find what it is congruent to mod 100.
Yeah.
Next.
So we can break this as 25 and
Yeah, so 100 is 25 times 4. So we
yeah,
should check for mod 4 and mod 25 separately, right?
yeah.
So for mod 25. So yeah. Yeah, Aman, continue.
Yeah, so here 25, the Euler's function value, what will be? It will be 5 into 4, it will be 20, and I think it will be 20, and it is
So for 25, what will be 20?
pi
This
of
remains
25 will be 20, I think. 5 into, yeah.
phi of 25. Okay, phi of 25. I don't know why we are calculating phi of 25. We could have directly calculated phi of 100, right?
Yeah, I of, but that will be little bit bigger, I think. I haven't tried this problem yet. So,
Or you can like cut all this. Like if you can try out with binomial coefficients too. Observe that 7 plus 3 is 10, right? So we can take advantage of that.
yeah,
So we can write 7 as 10 minus 3, and then this reduces to like 10 minus 3 per 100 minus 3 per 100. and then just like all the first 100 terms will have a 10 in them. So it's like 100 minus 10 power 99 times 3 times 100 and so on up till I guess it's plus 3 power 100, yeah, then minus 3 power 100. So these 3 power hundreds cancel out, and the term just before it is like 100 C99 times 10 power 1, 3 power 99. And observe this term. This term is basically 100 times 10 times whatever 3 power 99 is. So it has the first three digits 0. And similarly, all the rest of the 99 terms have 10 power, have 100 as their factor. So the first two digits are going to be zeros, right? So it's obvious that, yeah, so it would be congruent 0 mod 100. So we can directly infer from here that the first two digits are going to be 0. So the first digits or last two digits in whichever way you count are 0, 0. Or if you want to do it in Aman's way, so then we have to compute 525 for that. I guess it's 25 times 1 minus 1 by 5. So it's 5 times 4 or 20. So then we get 7 power 20 is 1 mod 25. Similarly, 3 power 20 is also 1 mod 25. So with this two piece of information, we can easily check 7 power 100 is also 1. So subtract them, you get 0. And for 4, I think it's the same way. So for 4, we have 5. 4 is 4 times 1 by 2, so it's 2. 7 squared is 49, which is 1 mod 4. And similarly, 3 squared is also 1 mod 4. So 3 squared is 9. And yeah, so it's 1 mod 4. And so 7 power 100 minus 3 power 100 is 1 minus 1 or 0 mod 4. Right, and then we can, from these two equations, we can conclude 7 power 100 minus 3 power 100 is 0 mod the LCM of 25 and 4, which is 100 in this case. So in that way, you can also proceed. So that's for the first problem. Wait, why are there two purple markers here? Okay, now it's okay. I need a green one. So second one. So here we have sum over phi d for all divisors of n. We have to show this sum up to n. Okay. So sum over phi d, we have to show this. So let's start with an example. So if n is some prime number, like say suppose 7, then the divisors of 7, let's call that set S. So S is the set of divisors of 7. So in this case, S is 1 and 7. And sum over phi 1, and so it's phi 1 plus phi 7. So what is phi 1? 1 is a single divisor, that is 1 itself. So 1, and phi 7 is, well, phi 7 is how much? 6, right? Since phi is a prime number, and for prime numbers, phi of any prime number is p minus 1. So they add up to 7. Okay, that's pretty obvious. Uh, okay, now let's divide, or let's split the set S into many small sets di, SDs, or SIs, maybe SIs. So what is SI? So SI is defined to be the subset or subset of S containing numbers with at most, not at most, with exactly a common factor, with exactly I as common factor with n. So like we check, okay, sorry, I defined the set S to be the set of divisors of n. So that is not this S. So let me call this S dash. So this set is just 1, 2, 3, 4 up till n, right? The first n natural numbers. So this is the first n natural numbers, S dash. And Si is like out of these numbers, some have GCD k and n. So GCD of k and n, if that is d, then that k goes into SD. So we get the collection of ki's. So k1, k2, k3 up till kr, suppose. So how many such numbers are there? So you can just use properties of GCD to infer that this thing here implies GCD of k by d and n by d is 1. Right, so both of them have only d in common. So if we divide d out, they are left with nothing. So they have nothing in common. So GCD is 1. And then you can treat this as a uh, as a prime number, and find how many numbers are there which are not necessarily a prime number. So number of such KDs equal to number of numbers less than or equal to n by d, and relatively prime to n by d. So what is the number of numbers which are less than something and relatively prime to it known as? As we had just learned in our previous class, that number is called the uh, Euler's totient function of n, or here in this case n by d. So we know the number of numbers less than n by d and relatively prime to n by d is phi n by d. So that means number of such k by d's is equal to phi n by d. And since number of such k by d, such and k by d's have a bijection with k's, the elements of the set St. So we get like the cardinality of the set St is actually phi n by d, right? So we found St, size of St. We don't need to know the elements right now, or yeah, right. So now this d is just one of the many divisors of n. So there are others d1, d2, and up to say suppose dl. So suppose let's look at the two sets sd1 and sd2. Do they have anything in common? Suppose there is an element x which is contained in both of them. Then what does that imply? So that implies GCD of x and n is d1 and d2 at the same time, since they are both in the two sets sd1 and sd2. So that can't happen. That's a contradiction. GCD is a unique and well defined, right? So this can't happen, right? This can't happen. So these two sets are disjoint. So sd1 intersection sd2 is null set. So d1, d2, d3 up to dl, they all define L many subsets S d1, S d2 up to S dl, who are all like all mutually exclusive. So intersection of S di, sorry. So intersection S di intersection S dj is null set for all I not equal to j. So one part of the puzzle is solved. We have shown they don't have intersections, so they are exclusive. Now we have to show they are exhaustive. That is, their union is S, or the set of first n natural numbers. So to show that, just pick anything like any x in S, right? And you see you can take a GCD of x and n, GCD of x and n. I defined SD as all those numbers which have GCD of exactly d with n. Let me add another restriction. So let me add it here. Ki is strictly less than or equal to n. Okay, so we are only taking numbers from S. So taking anything from S that will have a GCD with n, say suppose y, and that will place S in x in Sy. So all of them, all the elements of set S are in some element of Sy. So there exists y inside 1, 2, 3 up to L, such that for all x in S, x in S, x in Sy. So this whole thing implies union over Si's I in 1 through L is S. So basically, SDIs are mutually, sorry, I'm writing S like this, but it is SDI. I'm jumping one indent. So SDI. SDIs are mutually exclusive and exhaustive. So XDIs are mutually exclusive and exhaustive. So now what? So now we know that sum over cardinalities of SDI is equal to cardinality of S. And S, as we have defined, is just the first n natural numbers. So it has cardinality of n, right? And we also, yeah, so from here, so we know sum over SDIs is actually sum over phi n by d's is equal to n from star. Since we showed the cardinality of SDI is totient function of n by d. And now there is just a hand waving argument that says this n by di is a divisor of n itself. So when you divide n with a divisor of n, you get another divisor. So then you can just say for all divisors of n, dj, phi dj adds up to n. So that proves the claim. Okay, so any doubts? Did you get the argument? So constructing these STs was the crucial part of the argument. One would have to also observe that phi n by d is the cardinality of such SDs. SDs, yeah. Okay. So moving on to the last one. Before that, we need to know what is Wilson's theorem. So Wilson's theorem. Yeah, and even before that, we need to know what is multiplicative inverses modulo n. So what are multiplicative inverses? So for natural numbers, yeah, for natural numbers we don't have inverses. For real numbers or rationals, for reals, so x is suppose a real number, then we define multiplicative inverse of x as any number y such that x times y is equal to 1, the identity of reals. So one is considered the multiplicative identity of real numbers. So anything that gives that identity when multiplied with x is a multiplicative inverse of x. And since for real numbers we're used to writing the multiplicative inverse of x as simply 1 by x, so y is 1 by x. So now let's move back to our set of reduced residue, no, not reduced, the residue class, the complete residue class. So its elements are 1, 2, 3, 4 up till n minus 1 is the complete residue class of n. So, so let's take a concrete example. So for n equal to, say, suppose 6, we have 1, 2, 3, 4, 5 is the CRC for n equals 6. Now let's take x as 2. So can you find the y for this x such that we multiply up to 1 or xy gives remainder 1 mod 6? So let's try it out. So let's try to multiply 2 with all of them. So 2 times 0 is obviously not 1 mod 6. 2 times 1 is 2, which is again just 2 mod 6. 2 times 2 is 4, is still just 4 mod 6. 2 times 3 is 6, so that's 0. 2 times 4 is 8, that's also not the answer. And 2 times 5 is 10, right? So that's again 4 mod 6. So as it appears, 2 doesn't have a multiplicative inverse mod 6. So that means y doesn't exist here. Sorry. So there doesn't exist a multiplicative inverse mod 6, at least for the case of 2. But if you take x equals to 5, then you see 5 is the multiplicative inverse of itself. So take y equals to 5, then that implies x times y is congruent to 25, congruent to 1 mod 6. So if you divide the set, the complete residue class of 6 into numbers which have multiplicative inverses modulo 6 and which don't, then for the first set you get 1, then 5, just these two numbers. And for the second set you have 0 and 2 and 3 and 4. Right. So can you see the pattern for the first set? So these have inverses mod 6, these don't. So observe that these are also the numbers which have some GCD, like a GCD more than 1. So x and 6 have GCD more than 1. But this have a GCD of exactly 1. So GCD of x and 6 here is exactly 1. So why is this? Like, is it always true that whenever a number is not co-prime to n, then it doesn't have a multiplicative inverse mod 6 or mod n? So let's prove this claim. Claim Yeah, so claim is prove that uh, x in complete residue class of 6, not 6, for n has a multiplicative inverse mod n if and only if the GCD of x and n is 1. So how does this proof start? So let's first see this direction. This direction. So we have, or our assumption is, the GCD of x and n is 1. So GCD of x and n is 1, right? So we need to find y such that xy is 1 mod n. Basically, this argument is the same as the Euler's theorem one. So we have to construct the set, the reduced residue class of n. So reduced residue class of n. So that will have all the divisors, sorry, not devices, all the numbers a1, a2 up till a phi n. So phi n many numbers which are less than 6 and relatively prime to 6. This is by definition is reduced residue class of 6. And then we will argue that if we pick any number, say suppose x, yeah, x from this set. So we multiply the whole, each of the numbers from this set by x, okay, this x. Then we argue as before, so we're not picking x, so cut that step. So multiply the our whole reduced residue class with x, and then we get a new set, b1, b2 with bn, and then we will argue that any of the AIXs can't be equal to AJX mod n. Why is this true? Since that will imply AI x times AI minus AJ is congruent to 0 mod n. Now GCD of x and n is 1. That's what we have assumed. So that just leaves AI minus AJ with have to being 0 with n. And that means AI has to be congruent to AJ mod n. And added to the fact that all of them, all the AI and AJs are strictly less than n, so that will imply AI is equal to AJ. So here we had to assume AI not equal, yeah, AI not equals to AJ, right? So here we got AI is equals to AJ, so that would imply a contradiction, and then we will be forced to say that, so this can't happen. So yeah, so AIX and AJX can never be congruent, so this can't happen. So that will imply AIX and AJX. So each of the AIs, when multiplied with AJs, when multiplied with X's, will generate a new distinct BI, right? So this cardinality of the set, whatever set is generated, is also phi x, sorry, phi n, as before, as the reduced residue class of x. And then the next part of the argument is, yeah, so they don't generate anything outside of RRC. That is the next question. So so see, suppose AIX is congruent to some AJ mod n. What does that imply? So just a minute. So let's assume AI times AX, AI times X is something outside. So AI times X is congruent to Y mod n, and Y is not inside the reduced residue class of n, or it is not inside the set. So if that happens, so what is the definition of reduced complete residue class, or yeah, reduced residue class? So they are all the numbers which are less than n and relatively prime to n, right? Okay. Okay, so let's check the GCD of n and AIX. So then we know the GCD of n and x is uh, n and x is 1. Right, we assume that. And what is GCD of n and AI? It's 1 also by the definition of RRC. Since AI is in RRC, so since AI is in RRC of n, so these two will imply n and xai is forced to be 1. So those two also have GCD of 1. And that implies x times ai is forced to be inside RRCn. So even after multiplying the elements of RRC with x, we don't get anything outside of the RRC, and we get phi n many numbers, all of which are distinct. So that forces a times RRCn to be exactly equal to RRCn. Yeah, so that's the same argument we used in Euler's theorem. So that proves the if part. So yeah, so like this RRC always has a set 1, since 1 and n always GCD of 1, right? So we just we just wait, why am I using the orange color so much? So we just pick AI AIX congruent. So we pick I such that AIX is congruent to 1 mod n and set y equals to AI. So this always works. Whenever we whenever we need to find the inverse of anything of x mod n, we just look at the reduced residue class of n, multiply that reduced residue class with x, and since they result in a set which has 1, so the corresponding AI, which when multiplied by x gives 1, is the inverse of x. So we just proved the existence of AI. We didn't necessarily find a formula for reverse or back computing AIs, right? So this direction is proved. For the other direction, so for this direction, the onlave part, so now we know x is in the complete residue class of x and it has a multiplicative inverse. So we have complete residue class, no, not complete residue class. Okay, yeah, that was just our assumption. And GCD of x and n is 1. So these two conditions jointly imply x and n has x is in reduced residue class of n. Right, so x is in reduced residue class. We can just restate the proof for this part with x as the same x, and it works since we will anyways be using the reduced residue class. So this is done too. So that proves the whole claim. Qued. So claim proved. Right, so this claim is true as we supposed. So then that means, so this is an if and on leave statement, right? We proved both ways. So that means for this set, the reduced residue class of 6, they have a multiplicative inverse mod 6, but this set, what can I say, like the complete residue class of 6 without the reduced residue class of 6, I don't think this set has a name, but none of the numbers in this set are multiplicative inverse mod 6. So now let's move on to Wilson's theorem. Before that, I just wanted to point out some note for prime p. So for all prime numbers p, the reduced residue class of p is actually equal to the complete residue class of p, since both of them is this set 0, 1, 2, up to p minus 1, since all the numbers are relatively prime to p, which are less than p. So only in that special case, so that implies for all x in n, there exists y in n such that xy is 1 mod p. So each natural number actually has a inverse in this case when the divisor is a prime number. So using that, we proceed to Wilson's theorem. So it says primes for all primes p, we have p minus 1 factorial congruent to minus 1 mod p. So why is that true? So you can check that p minus 1 is congruent to minus 1 mod p. This is obviously true since p is congruent to 0 mod p, so we are just removing p. So that means we can like write p minus 1 factorial as p minus 2 factorial times p minus 1 factorial, so p minus 1, and that is equals to minus p minus 1, p minus 2 factorial. That is congruent to minus 2 by this theorem, by the claim of this theorem. So that means this is equivalent to showing, so equivalent to proving p minus 2 factorial is congruent to 1 mod p. So how to show that? Pretty easy, just consider the RRC or CRC, which is same in this case. So the complete residue class mod P and the reduced residue class mod P are both here 0, 1, 2 up till P minus 1. And we know each of them have an inverse. So we can just pair the inverses with the numbers here. Just a minute. I think I wrote 0 here. Oh, yeah, so reduced residue class and complete residue class are not exactly equal since 0 is not there. So this is wrong exactly. So this is, I should write in this side. So union 0, then you get the set with 0. So let's start with the reduced residue class mod P. So this set, so basically P minus 1 factorial is the product of each of the elements of this set. So x inside the RRCP. Right, so x is p minus 1 factorial is the product of elements of this set, and we can pair the set, each of the element of this set with their inverses. So if we try to do that, then we can observe one thing. So observe that p minus 1 times p minus 1 is congruent to minus 1 times minus 1 is congruent to 1 mod p. So p minus 1 is the multiplicative inverse of itself. So p minus 1 is the inverse of itself or a self-inverse. Right, so p minus 1 is a self-inverse mod p. There is another one. So 1 is also a self-inverse self-inverse mod p. So we have two self-inverse in here, 1 and p minus 1. There may be others, but we don't need them. Just like, just observe that if we club, or if we just remove these two numbers from p minus 1 factorial, so okay, so what is the product actually congruent to. So you see, p minus 1 factorial is basically equal to the product of each of the elements in the reduced residue class of p, and that is equal to, if we club the inverses, so it's x times x inverse. Uh, how should I write it? Like I, so it's x1 times x2 inverse. No, not. You can take the square and then it would be easier for us to write. So let's take the square for the moment. What happened? X times x inverse for x in RRCP. That's one mod, mod P. Just a minute. Okay, yeah, that is one. But so you see, for all the, if we leave out p minus 1, okay, so let me leave out p minus 1. So up to p minus 2, let's call this set A. So the product over A is equal to p minus 2 factorial, and like we can leave out 1 again, since 1 is the inverse of itself and it is anyway congruent to 1 mod p. So we are left with 2 up to p minus 2. So that's even number of things, I suppose. Yeah. So we can club 2 with its inverse, 3 with its inverse, and like that. So this is just 1 mod p again. Yeah, so that's how we prove p minus 2 is 1 mod p. Remember, we just needed to prove p minus 2 factorial is 1 mod p. So that's done. So Wilson's theorem is just that p minus 1 factorial is congruent to minus 1 mod p, or p minus 2 factorial is 1 mod p. They are both equivalent statements. So going back to our original problem, we needed to show r times r factorial sum over r equals to 1 through n minus 3 is 0 mod n, right, if n is prime. Okay, so how can we write r times r factorial in a more compact way? So r goes from 0 through n minus 3. Just add and subtract r factorial. We get r plus 1 factorial minus r factorial. Uh, yeah. So then we can write the, so this r runs from 0 through n minus 3. So plugging 0, we get 1 factorial minus 0 factorial. Then we have 2 factorial minus 1 factorial, 3 factorial minus 2 factorial, up till n minus 2 factorial minus n minus 3 factorial. Right, and then we can cancel out diagonally like this. So we are left with n minus 2 factorial minus 0 factorial. 0 factorial is 1, as you know. It's an interesting question. Now, why 0 factorial 1? So this is 1 here. Why is 0 factorial equals to 1? So can any one of you suggest how to prove this? Like, how is 0 factorial 1? Or do you think it's a definition or arbitrarily a set to 1? Anyone? Shonok? Can you prove why 0 factorial is 1? Hello, I'm audible. Shonok. It seems Shonok is not here. So, Srujan, can you unmute and reply? Srujan? Okay, whatever, let me continue. So why is 0 factorial 1? So 0 factorial, you see you can write n factorial by n plus 1 factorial as 1 by n plus 1, right? So we can use this as a definition of factorial. So n factorial is n plus 1 factorial by n plus 1. This is the definition of n factorial, a recursive one. So if we put 0 in here, so it's 0 factorial is 1 factorial by 1, so it's 1. So that's just a short proof of why 0 factorial is 1. So continuing here, sum over r times r factorial turns out to be n minus 2 factorial minus 1. So therefore, sum over r times r factorial, r runs from 0 through n minus 3, is congruent to n minus 2 factorial minus 1 mod n. And what do we need to show? We need to show this is 0, right? When if and only if n is prime. So let's see this side. So if part, assumption here is n is a prime. So n is prime, and from Wilson's theorem, so we can apply Wilson's theorem since n is prime. So from Wilson's theorem, n minus 2 factorial is 1 mod n. So that implies n minus 2 factorial is, or n minus 2 factorial minus 1 is 0 mod n. So done. So this side done. The reverse side, only if part. So here we have n minus 2 factorial is congruent to is congruent to 1 itself. Mod n, we have to deduce whether or not n is prime. So what is the statement of Wilson's theorem? So for all primes, I guess Wilson's theorem is so Wilson's theorem is only one directional, so we can't use that here to infer n is prime. So just think of something else. Let's see. I think Wilson's theorem is the strong one. Like it says if and only if only. Just let me just wait a minute. I'm checking. Isn't it clear from our proof? So what is our proof? So the proof of Wilson's theorem relies on the fact that the product of the numbers from 2 up till p minus 2 is 1, mod p of course. And that is true since the set 2 up till p minus 2 is like each one of them have its inverses present in this same set, and they are distinct. I guess we just need to prove the distinctness of the inverses or the uniqueness of the inverses. So why are the inverses distinct? So let's assume they are not. So x1 and x2 have the same inverse y. So x1 and x2 is congruent to 1, congruent to x2y mod p. Say suppose, right? So then of course we can divide both sides by y, and since y and p is GCD 1, so x1 is forced to be congruent to x2 mod p. And this is a contradiction since we assume there are two distinct uh, residues x1 and x2s which are less than p and have distinct inverses mod p. Right, so that means this is a strong statement. So this happens. So p is prime if and only if p minus 1 factorial is minus 1 mod p. This is an if and only if statement. Right. So this thing follows from the only if part also follows from Wilson's theorem. Next, let's move on to. I remember one tricky problem, one setup in RMO, so let's solve that. Wait a minute, let me see if I can find that. Is it 2011 or something? Okay, till I find that problem, you guys solve this one. So this one is prove the sum of the n digits. So show that 121 doesn't divide n squared plus 4n plus 5. Oh, sorry, not 4n, 3n plus 5. So solve it for 5 minutes. Then I will, in the meantime, I will try to find that problem that I just remembered. Okay. Okay, so around 7-8 minutes have passed. So, anyone, any breakthrough with this problem? So, this is a tricky problem. So, you have to first factorize this part. As you can see, you can't directly factorize this, so just add and subtract 33 plus 33 and minus 33, or minus 33 and plus 33. So it's minus 28, I suppose. So this is the crucial step, and pretty unintuitive at first, but you will see why this works. So next, middle term factorization. So you have to divide, so find two numbers, of course 4 and 7. Uh, so they add up to 3, subtract and give 3. So 7 minus, let me write directly, so n minus 4 times n plus 7 plus 33. Now what? So now just look for divisibility by 11. So check for divisibility by 11. Say suppose 11 divides n squared plus 3n plus 5 minus 30, no, minus, yeah, so just this. So for 121 to divide the original expression, 11 must at least divide the expression, right? So that would imply 11 divides n squared plus 33, 3n plus 5 minus 33, minus 3 times 11. So that implies 11 divides n minus 4 and n plus 7. So 11 divides the product of n minus 4 and n plus 7. And observe these two factors are exactly so 11 apart. So these factors are 11 apart. That is 11 n minus 7 n plus 7 minus n minus 4 is 11. So if 11 divides any one of them, 11 divides any one of them, 11 divides both. Why is that true? Since 11, if 11 divides any one of the factors, call the first factor capital A and the second one capital B. If 11 divides capital A, that implies 11 divides capital A plus 11, which is exactly equal to B. Right? Capital B is capital A plus 11. So it's basically equal to A times A plus 11. Since they are 11 apart, 11 divides 1 implies it divides the other. So if so yeah, so what do we get? So if 11 divides the whole thing, If 11 divides the whole thing, then 11 has to divide either 11 has to divide the first factor, the product of the first two factors, and then if 11 divides any one of them, it divides both of them. So 11 square divides 121 in any case. Since 11 is a prime number, it can't partially divide in one of the factors, and the rest of the factors of 11 are in the other one. So that can't happen. So basically, 11 square divides the product n minus 4 times n plus 4. So now we have, so now just move back and look at the original problem. N squared plus uh, 3n, n squared plus 3n plus 5, which is equal to n minus 4 times n minus n plus 7 plus 33. So we have shown 121 divides this thing, and we want to prove 121, or we can, if you have assumed 121 divides the whole thing, so that means 121 has to divide the second term, that is 33, which is a contradiction here, since 33 is smaller than 121, so 121 can't divide 33. So 121 has to divide 33 for n square plus 3n plus 5 to be divisible by 121, which is a contradiction since 33 is less than 121, and that proves why we why 121 can't divide the numbers of the form n squared plus 3n plus 5, n integer of course. So that's it. That's that problem. Next, before we move on to Chinese remainder theorem, let's solve yet another one. Hmm. Okay, so show that it's a new question. 641 divides 2 power 32 plus 1. Let's try this one for the next 5 minutes. Okay. Okay, so this is not that easy problem to like to approach, since yeah, you if you just want to like simplify and try to find some power of 2 which either is equal to minus 1 or plus 1 mod 641, then that's a good approach, but it will take some time. A more elegant ways is probably to like observe this is the fifth format numbers. So what is the format numbers? So format primes. Yeah, so format primes. So numbers of the form 2 power n plus 1 are called format primes. Yeah, and well, don't get fooled, they are not exactly primes. Uh, 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 I guess he was a French mathematician, yeah. So Fermat, a French mathematician, once conjectured that these numbers 2 power n plus 1 are all prime numbers, right? So he just conjectured that he had found a sequence of prime numbers, which is extremely rare discovery, or which he also became famous for. But unfortunately, his conjecture turned out to be incorrect, as Euler, one of his like rival mathematicians back in Germany, soon found out or discovered that 2 power 5 plus 1, that is the fifth format number f5, equal to this number over here that we want to show is actually divisible by 641 and hence not a prime number, is composite. So f5 is composite was shown by Euler. So how did he prove that f5 was composite? Well, he observed two things. First, 641, which is also not a prime number, can be, uh, or I mean, not a prime number. It is a prime number, right? But it can be decomposed as 5 power 4 plus 2 power 4, and it also can be decomposed as 5 times 2 power 7 plus 1, right? 5 times 2 power 7 is 640. 2 power 7 is 128, and 5 times that is 640. So 641 has these two decompositions. Now multiply this thing with 2 power 28. So we get 5 power 4 times 2 power 28 plus 2 power 32. So this thing is 641 times 2 power 28. This implies 641 divides 5 power 4 times 2 power 28 plus 2 power 32. Call this number capital A, suppose. 6 divides capital A. Now with this number, we can we can use this root factor theorem. So this is called root factor theorem. So it says x plus 1 divides x power n plus 1 power n, or basically x to the power n plus 1 is divisible by x plus 1, and x minus 1 divides x power n minus 1. Sorry, actually I reversed it. This is minus, this is plus. So this is, I guess, comes from the expansion of x power n plus 1 equals to x minus 1 times x power n minus 1 plus n minus 2 plus dot 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 up till 1. Okay, so that's the expression, and x power n minus 1 is x plus 1 times x power n minus 1 minus x power n minus 2 plus x power n minus 3 minus up till minus 1 power n minus 1. So I guess this expression only holds for an odd, only true for an odd, but this always holds. So true for all n. And we need the first one here in this case, right? So we need x plus 1 divides n x power n minus 1. So why is this? Yeah, so how can we use this? So we can put x equals, plug x equals 5 times 2 power 7 in this equation. So 5 times 2 power 7 plus 1 divides 5 times 2 power 7 whole power. So what is the power? 4. Yeah, 4 minus 1. So this is true since 5 times 2 power 7 whole power 4 is 5 power 4 times 2 power 28. These first two terms are same, so that's why we are taking power 4. So this follows from root factor theorem. This is that alleged theorem. Okay, so and how does this help us? Well, this is just disguised 641, right? So this says 641 divides this new number b 5 power 4 times 2 power 28 minus 1. Call this number b. So now we have 641 dividing a and 641 dividing b. That is, they divide their difference. So a minus b is also divided by 641. So this implies 641 divides our required number 2 power 32 plus 1, which is their difference, right? So that was a pretty clever way to prove this problem. Well, this exact same method may not be used by Euler, but that was what written in Hardy and Wright's book in theory of Hardy's theory of number theory, Hardy's number theory book. It's a pretty thick book. If you get time, you can check it out. I guess I had listed that one too in my book lists. Okay, so let's call it a day now. Let's end this class over here. Only we will discuss Chinese remainder theorem next day. So continue from here. I'm not explicitly giving any problems and exercise. So just try and solve exercise 1.1 and 1.2 from excursion. From excursion as your homework. Okay, so good night, everyone. Meet you next week. Try to solve the problems of excursion, the first two exercises only. Okay, bye.